In this video, I will review the questions that were given to you on the practice test for test number 2. I'm going over every problem in this. However, you may not need to go over every problem, so feel free to fast forward through parts of this video to get to the problems that you want to review the most, because this is a lengthy video. So the first problem you were given on this practice test was to determine the prime factorization of a couple of numbers. And this is the basis for being able to find lowest common denominators or greatest common factors or greatest common multiples, whichever way you want to look at them. And that's basically being able to take any number and write it as a product of prime numbers. And so, for instance, for 336, now how I get this split up might be different than how you did it, but keep in mind, that in the end, as long as you get the same prime factors and the right numbers, that's what we're looking for here. So 336 is the same thing as 16 times 21, neither of which are prime numbers. And so I break them down further. 16 I make 4 times 4. 21 I make 3 times 7. It just so happens that 3 and 7 are prime, but the 4s weren't. And so I break them down further into 2 times 2 and 2 times 2. All the 2's are prime numbers. And so what I have here is 4 2's being multiplied together, 1 3 and 1 7, when I can write it that way. Oftentimes, though, when we do prime factorization, we write that using powers, so I'm going to have 2 to the 4th power times 3 times 7. And when I look at 2,520, 252 times 10 is one way to break it down. When I break it down further, 2 and 5, which are prime, 9 and 28 are not. So 2 and 5 are going to stick around. The 9 and the 28 are going to break down further. That's going to be 9 is going to be 3 times 3. 28 7 times 4. The 3, and the 7 are prime. The 4 still is not. So these are going to stick around. I'm going to break this down further into 2 times 2. And those are prime numbers. And as you can see now, we have 3 2's being multiplied together, 2 3's being multiplied together, a 5 and a 7. So I could write it that way, but I could also write this as there's 3 2's being multiplied together. That could be 2 to the 3rd power. 2 3's being multiplied together could be 3 to the 2nd power, or 3 squared. And so I have 2 cubed times 3 squared times 5 times 7. In this next problem, we're taking it a step further. As I mentioned before, we're going to find the GCF, or the GCD, whichever way you want to know it, of the following pairs of numbers. So what we're going to need to do is figure out the prime factorization of each number. And then with those, we can find out what the greatest common factor or greatest common denominator is, or divisor. So 96, I'm showing the entire tree. I'm not going to go through it step by step. But as you can see here, it comes down to being 5 2's being multiplied together times 3. 224, there's the prime factorization, there's the factor tree. It comes out to 2 to the 5th power times 7. Now, the greatest common factor, when I look for that, should contain everything that's in the highest power of each prime factor that's in both. And so when I look at these, the 2 to the 5th is in both of them. So both of those, so the GCF is going to have 2 to the 5th in it. This has a 3, this doesn't, so 3 is not going to be in there. 7 is in this one, but not this one, so that's not going to be in there. So the greatest common factor, or GCD, is going to be 2 to the 5th power, or 32. In a very similar manner, we'll look at 144 and 528. The prime factorization of 144 is 2 to the 4th power times 3 squared. For 528, it's 2 to the 4th power times 3 times 11. Now, as I look at the prime factors, they both have 2 to the 4th power, which is great. So 2 to the 4th power will be part of the greatest common factor. This one has a 3 squared, this one has a 3 to the 1st. So the highest power of that factor that both of them have is 3 to the 1st. And this one has an 11, this one doesn't have anything like that. So basically, the greatest common factor is going to be 2 to the 4th power, which they both have, and 3 to the 1st, which they actually both have. I mean, if I have 3 squared, I do have at least one. I have 1 3 there, being multiplied. I actually have 2, but at least there's one that they have in common. So And 2 to the fourth power is 16 times 3 is 48. So that's the greatest common factor. That's the biggest number that'll divide out of 144 and 528. When I look for the least common multiple, I'm going to start off the same way. I'm going to be starting off finding using these factor trees to find the prime factorization. So for 27, that's 3 cubed. For 36, that's 2 squared times 3 squared. Now, when I look for the least common multiple, I want to find, you know, basically the highest power that's in any one of them. So when I look at here and I see the 3 to the third power and the 3 squared, I'm going to take the 3 to the third power. And this one has a 2 squared. This doesn't have any 2's at all, so I'm going to take 2 squared. So the least common multiple is going to be 2 squared times 3 cubed, which is basically the same thing as 4 times 27, which is 108. For 540 and 2250, here are the prime factorizations of those two. And so when I look at these two, 540 has a 2 squared, 2250 has a 2. So I'm going to take the highest exponent of those, which is going to be 2 squared. So the least common multiple is going to have 2 squared as part of it. This one has a 3 to the third power. This one has a 3 squared. The least common multiple is going to have the 3 cubed in there. And I have a 5 here and a 5 cubed. The least common multiple is going to have the higher exponent, so it's going to be 5 cubed. So the least common multiple is going to be 2 squared times 3 cubed times 5 cubed, which is 13,500. And this works despite how many you have in front of you. Like for instance, number 4, you were asked to find the least common multiple of 30, 90, and 150. So it's the same way. I'm just going to take the 3 numbers, find their prime factorizations, and then I'm going to look at all 3 of them and find the highest power of each prime factor I can get. So this one has a 2, a 2, and a 2. So the highest power of 2 that any one of them have is just 2. This one has a 3, this one has a 3 squared, this one has a 3. So the highest power of 3 that I see is a 3 squared. So I'm going to choose 3 squared, and of course 5, 5, and 5 squared. I'm going to choose the 5 squared. So the least common multiple is going to be 2 times 3 squared times 5 squared, which is 450. When I do the greatest common factor, or GCF, for it, the same thing. I'm going to take the 3 numbers and find their prime factorizations. I'm not going to go and spend too long going on those. And here I want to find basically the lowest power of each one. That's where some people get confused with these. When I look for the least common multiple, I'm looking for the highest power any one of them has, whereas the greatest common factor, I'm looking for the highest power that all 3 have, which means I'm basically looking for the smallest exponent that amongst the 3 of them. So if I have like a 2 and not a 2, well, the greatest common factor is not going to have a 2 in it. So, so here, when I look at these 3, this one has a 2 squared, this one has a 2 squared, and this one has a 2 cubed. And so, I'm going to take the 2 squared in this case. This one has a 7, this one has a 7, this one has a 7. So the greatest common factor is going to have a 7. This one has a 5, the other ones don't, so 5 is not going to be included in any way. And 3's in this one, but not in the other ones, so it's not going to be included in any way. So whereas if it was the least common multiple, I'd be taking the highest power of the 2. I'd be using the 7 still. I have the 3 and the 5 as part of it because, I'm looking for what's in any one of them in the highest, exponent as well. So as I said before, for this case, the greatest common factor is going to be 2 squared times 7, and that's 28. So that's what the least, the greatest common factor for this is. Now, problem number 6, we start getting into these other types of number systems, and you're not going to be responsible for knowing the the various symbols and what they represent as much as knowing, the more, general information about the numbering system. So for instance, we're trying this number 62,372, and we want to write this in an Egyptian format. Now, an Egyptian is just one of those numbering systems which is basically like an addition numbering system. So when I look at the symbols that could be used. I'm going to try to break this down into saying I'm going to have, some number plus some other number plus some other number down the line in order to get this. And you see the symbols that we have here, they're in basically powers of 10. So, I'm not going to be using the astonished person because that's a million. This is only 62,000. I'm not going to be using the tadpole or whale. I am going to be using the pointing finger, I am going to possibly be using the lotus flower and so forth down the line. So when I look at this, I want to be able to break this down into, its various, and for Egyptian, this is very similar to like our numbering system and identifying sort of the place values. Because I have basically here 60,000 plus 2,000 plus 300 plus 70 plus, and it looks like part of it got lopped off here. So, but it's basically 2. So, and so when I get down to here, I'm going to have six 10,000s plus 2 1,000s plus 3 100s plus 7 10s plus 2 1s, or 6 pointing fingers, 2 lotus flowers, 3 scrolls, 7 heel bones, and 2 staffs. So there's the 6 pointing fingers, there's the 2 lotus flowers, pardon the drawing of them, I don't get the chance to write in Egyptian all that frequently. There's 300, 70, and 2. And so that's how you would write it. Now, you can also write this in multiple lines as well. Just keep that in mind. They didn't really care. And also for Egyptian, you don't necessarily have to have them written in the order of their place value either. I mean, these are written in any order. They would still add up to be the exact same number. And therefore, that was one of the shortcomings of the system, is that, you could have a sequence of symbols represent the same number as another sequence of symbols, because they were put in different orders and things like that, which is a little bit, and that to us is like doing like, a 1 and a 2 and then a 2 and a 1. One says 12 to us, one says 21. Those are two different numbers for us. So, the next one was traditional Chinese. In a very similar notion, it's very similar to Egyptian because you have symbols, for your digits up until up through 10, and then after that it's basically in the hundreds, thousands. It doesn't go up very much higher as far as what we were given in this textbook. I mean, I'm sure there are symbols for higher values in the long run. But for this, and we have this really complicated 0 over here. Thankfully, this didn't really require a 0. But again, when I look at this, I had to start looking at, the fact that, I might need a 10,000 with this to make my life a little easier. Otherwise, I'm going to have to, put a 60 with a 1,000 with this, or a 62 with a 1,000. So, I happened to look it up, and I'm not expecting you necessarily to look it up either. But I think I did put it in the problem that the fact that this symbol here does represent 10,000. And so with this being the case, I can now make this a little easier on myself because I have 6 10,000s, 2 1,000s, 3 100s, 7 10s, and 2 1s. And, kind of similar to what I have written right over here. And, in the Chinese system, that's how I would say it. I'm going to write a 6, and then the symbol for 6, and then the symbol for 10,000. The symbol for 2, and then the symbol for 1,000. The symbol for 3, and then the symbol for 100. The symbol for 7. So down the line. So, and that's where I get these symbols here. 6 is this symbol here. Again, notwithstanding some of the difficulty. This is the newly found 10,000 symbol. 2 1,000s. So I'm going to have a 2, and then this symbol here for 1,000. I'm going to have a 3, which is this symbol here, and then this symbol here for 100. Again, I'm not the best at drawing them. So I don't have a lot of practice drawing Chinese. I'm going to have 7 10, so 7, and then followed by this. And then I'm going to have 2 1s, which is just going to be that symbol again. And so there is the traditional Chinese number for 62,372. Now getting to Greek, and making use of these symbols here, if I can get it to show up. I'm still going to be using the same kind of general premise: 60,000 plus 2,000 plus 300 plus 70 plus 2. Um, it's just that they actually have a few more numbers that represents things. They have specific hundreds and things like that. If you want to start getting to thousands, you use the iota symbol, which is this symbol right here, but you put it into a raised position before the number to indicate that. So if I wanted to indicate 60,000, I'm going to go to the symbol for 60, which is this symbol right here, um, chi. I think that's chi. Or Z. I'm bad with my Greek lettering names. So if I'm going to have this with an iota symbol next to it, when I do the 2000, I'm going to have this symbol with the iota symbol in front of it. And then I get on the line, the 300, which is the tau, the 70, which is the omicron, and the 2, which is the beta. And so you can see that is what the Greek equivalent of that number is as well. There's other little tidbits about Greek numbering. I mean, this book does simplify it a bit more than it actually is. So keep that in mind, that you're not necessarily going to be able to decipher Greek numbering exactly with what the book has here, but you can get pretty close with what it's saying. Roman numerals. So again, our Roman numerals that we're familiar with is up to here. Dealing with 60,000 could be a little bit on the tricky part, because I mean they really only go up to thousands. I mean, Romans didn't really have a number to represent millions, anything beyond that. But as I do this, I have to kind of keep in mind that looking at the 60,000, the 2,000, the 3,000, the 70, and the 2, I don't know how to represent these things. So I'm going to look at 60 10,000s, 1,000 plus 1,000, and what I'm trying to do is put this in an order which I can, write the symbols that go next to them. Plus 100 plus 100 plus 100 is 300. 70 is 50 plus 10 plus 10. And 1 plus 1. If I have any numbers with 9s in them, that's what I have to, or like even some numbers like with 4s in them, because like for the 50 and the 500, I have to be aware of the subtraction convention with that. Instead of saying like x x x x for 40, I would say XL for 40. So I have to keep track of those as well. So for 60,000, I'm just going to write the number L. I'm going to write the number LX, which is L plus an X following it would be 50 plus 10, which is 60, and a bar above it indicates 1,000. And so this is 60,000. The two 1,000s, I'm going to have two M's following that. The 300s following that is going to be three C's. 50, which is L, two more 10s, which is X and X, and then two I's to represent that number. So remember that the bar above the Roman numerals indicates that's in thousands, and that you'll be okay with that. The Babylonian and Mayan systems are much more place value-ish. And the tricky part about that is that the Babylonian and Mayan systems don't work at the same place values we have. We have place values of 10. And you can even see to a certain extent that the traditional Chinese symbols it comes very close to that. The Greek and the other ones not so much, because they have many different symbols and they write out different things to represent these numbers. The Babylonians only had 3 symbols. And here they are. I mean, again, you have this symbol for 1, this symbol for 10, and this symbol to indicate a subtraction. And the other tricky part about the Babylonian system is knowing that it's a base 60 system. So I have to be aware of my powers of 60. And so I'm not counting 60 to the 0 power. That'd be my units power. 60 to the 1, of course, is 60. 60 squared is 3600. 60 cubed is 216,000. So I'm not going to need any 60 cubes. So, as I try to break this down, I got to figure out what numbers get divided into, 62,372, and then the remainder of that, and the remainder of that, in order to break this down into its rightful parts. And so when I do 62,372 divided by 3,600, I figure out that I do have 17 60 squares, and then I have a leftover number. That leftover number will go into, it can be divided by 60 19 times, and then I'm left over with 32. So basically I have, this would break down to 17 times 60 squared plus 19 times 60 plus 32. And the way I represent this, I mean, these are my place value areas. I'm going to have 1760 squares, which means I need to come up with a number for 17, which essentially is, this symbol here. I mean, I've seen it written in different ways, but usually if you're over halfway, you'd use a subtraction. So I just, instead of writing like one of these and then 7 of these, which is still somewhat valid, I wrote 2 of these, which represents 20, minus 3, which is 17. And that's in that position. That's the 60 squares position. I want to leave a space, a gap, and go to the next position, which would be my 60th position. So I want to write the number of 19, which is going to be very similar to this, except I'm going to have these two symbols, subtraction, and then just 1. And so I have 1960s, and then I'm going to leave another gap to indicate a place value, and I'm going to have 32, which would be 3 of these and 2 of these. And so this is telling me I have 17 60 squares, 19 60s, and 32 units, which would come out to be 62,372. With the Mayan system, we use this numbering system here. Not too hard to remember either. Some of these aren't showing up really super. I mean, this is a much thicker bar than it should be, but that's okay. Because remember, a horizontal line represents 5, a dot represents 1. So if I have 2 lines and 3 dots, I'm going to have 2 5s and 3 1s, which is going to be 13. I mean, that's not too hard to do. It's just representing the fact that this is a base 20 system, which goes along with the fact they only have 20 symbols here, including the 0. So for the number 62,372, you're going to first figure out how big these numbers can get so you know which place value to start with. And as you can see, 18 times 20 to the third power is over 144. It's 144,000, so that's much too big. So that one's going to be left out. So the first place value is going to be the 18 times 20 squared position, and that's equal to 7,200. So you want to see how many times that goes into 62,372. And as you work it out, it goes in 8 times, you'll get a remainder, and then the number you're left over with goes into 360 13 times, which gives you a remainder, and that number goes into 20 4 times and gives you a remainder of 12. So this is the breakdown that you would see with that, which means that these are the values of the numbers here that you're going to see in the place values. So you're going to have the 8, the 13, the 4, and the 12 in those positions. And so those will be your numbers. In the next problem, in 7a, you have a Mayan representation of a number, and you're asked to state what the number actually is. So you have 2 in the 18 times 20 squared position. You have 13 in the 18 times 20 position. You have 10 in the 20 position, and you have 14 in the ones position. So these are the positions. their place values, and that's the number being multiplied to them. So to figure out the value of this number in Hindu American, you're going to have 2 times the 18 times 20 squared plus 13 times the 18 times 20 plus 10 times the 20 plus 14, which works out to be these values, and you end up with 19,294. Traditional Chinese, same thing. When I look at this, I have this symbol here, which means 5. This goes along with 1,000. So I have 5,000, 700, 2 tens, which would be 20, 9. So 5 1,000, 7 100s, 2 tens, and a 9, which would give me 5,729. So pretty straightforward with that one. This one here, again, I'm just going to add up the numbers. So I have omega, z, and this is gamma. So this is 800 plus 60 plus 3 based on the symbols you see in this table, which is 863. This one here, theta, is 9, but this 9 has this iota in front of it, which means that's 9,000. This this symbol here, chi, goes with 600. This is kappa, I believe. Kappa? Yeah, I think it's kappa. That goes along with 20. And this symbol here is eta, which goes along with 8. So I have 1,600 plus 20 plus 8, which is 9,000. Otherwise, I have a 5 here all of a sudden. That'd be 628. Let's make sure. Yeah, it should be an 8 down there. So let me change that really quick. That should be an 8. Let's make this a little brighter. Because that should have been an 8 as well. So I just made some copying error along the way. So it should be 9,628. On to the next one. We're given the Babylonian symbols again, and these. So again, remember that Babylonian is a base 60s system. This is this first one here is my units. This one here is, let's get back to my pointer. This is the units. This is my 60s. This is my 60 squares. And so when I look at these numbers, this number here is 40 minus 2, so that's 38. This is 20 and 3, that's 23, and this, of course, is 32. So I have 38 60 squares, 23 60 to the first powers, and 32 60 to the zeros, which is just 1, so 32 ones. So I'm going to have 38 times 60 squared plus 23 times 60 plus 32, which equals these numbers here, which totals 138,212. For this one here, given these Egyptian symbols, and given these over here, I'm going to translate this number. So I have 3 astonished persons. That's 3 million. I have 3 times a million, plus 100,000, plus 2 10,000s, plus 1, 2, 3, 4 100s, plus 6 10s, plus 3 1s. And so this is what I read off before. So we can see what I'm counting and everything. And so, and 3 1s, of course. And so that's going to be 3 million plus 100,000 plus 20,000 plus 400 plus 63, which is 3,120,463. For the Roman numerals, this one here, these are 2,000s. That's a 100, but it's it's preceding a number higher than it. Typically, numbers should be going in highest order to lowest. In Roman numerals, if I have a number smaller than a number that comes after, that means that I'm using that subtraction convention. I can only use C's, X's, and 1s for subtractions. And so this means I'm taking 500 minus 100, which is 400. Here, X is 10, L is 50. So again, this is a smaller value preceding a bigger value. So this is 40, and that's 7. So 2,447. So 2,447. For this one here, I have this part underneath the bar. Okay, so this is 50. This is 10, 3 tens, that's 30 more, and that's a 5. So I have 50 plus 35, that's 85. So I have 85,000. CD again is 400, XL is 40, and IV is 4. And so I'm going to have 85,444. These are just asking you to convert into base 10 numbers. Now, the converting to base 10 is a little bit easier than converting from, just like some of the stuff we did with those numbers we just looked at. For a base 2 number, I have to remember this is my units, this is my 2's, 2 squares, 2 cubes, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, 2 to the 9th power. And so I have 1 2 to the 9th, no 2 to the 8th, 1 2 to the 7th, 1 2 to the 6th, 1 2 to the 5th, 1 2 to the 4th, no 2 to the 3rd, no 2 squared, a 2 and a 1. And so I would add these all together. I'm going to have 2 to the 9th plus 2 to the 7th plus 2 to the 6th, all the way down the line, getting rid of the zeros. That's what they come out to be, and that totals 755. So that's a pretty long number to write 755, but it is binary. This is base 6. So this is my units. This is my 6's. My 6 squares are 36's. My 6 cubes, my 6 to the 4ths. And so when I break that down, it's 2 times 6 to the 4th, 5 times 6 cubed, 1 times 6 squared, 4 times 6, and 2, which gives me these numbers all added together, which is 3,734. Same thing with base 12. This is my units. This is my 12s. This is my 12 squares. This is my 12 cubes. So I have 8 12 cubes, 9 12 squares, 5 12s, and 2 1s. When I multiply these through, I end up getting these numbers. And then when I add those through, I get 15,182. When I have numbers that are over base 10, obviously, we only have, we're using the same symbols, but we only have, 10 digits in our system. We don't have any other digits to use. So what's tend to be used, if I'm using a base system that's over 10, is I start using letters of the alphabet to take the place of, a numeric value, but it's being used as a digit. So 8 represents 10, B represents 11, C represents 12, so forth and so on. And so when I look at these numbers here, the 5, the 4, and the 9 still represent 9s. The D is 13, the E is 14, and F is 15, I believe. And so this is my 1s, this is my 16s, my 16 squares, my 16 cubes, my 16 to the 4ths, my 16 to the 5ths. So I have 15, 16 to the 5ths, I have 5, 16 to the 4ths, I have 14, 16 cubes, 4 16 squares, 13 16s, plus 9 units. And that's what the numbers come out to be. When I add it all together, I get 16,114,905. When I convert from base 10 to another system, that's where it gets a little bit more complicated, because I have to kind of remember the place values. So again, at base 5, I'm going to have each place value represent, a multiple or a power of 5. So I'm going to look at the powers of 5s that might be involved with this. I can see that 5 to the 1st, 5 squared, 5 cubed, 5 to the 4th, which is 625, can all be involved. I get 5 to the 5th. That's too big. I'm not going to have any of those involved with 879, so that one's gone. And so I carry through the divisions. I do 879 divided by 625, it goes through once with the remainder of 254. I take that 254 and then now divide it by the 5 cubes, or 125, and that goes in twice with a remainder of 4. I would then divide by the 125, but essentially Well, I have this going all the way down. I mean, this should be 25. You can kind of see what's going on here because it's and then it doesn't go on through here either. So um, yeah, this is off by one. There should be an extra zero in there. So this number should actually be. Let me change the color on this because I needed to do a division here as well. No, I did the 125. I'm sorry. I just have I should have a division of the 25, which would have been 0, which is still would have given me my remainder of 4, and then I would have come to this. And so I have 5 ones, I have no 5s, I have no 20, so there should be a 0 here, and then the 4 here. 99 in base 3. I look at the powers of 3. 243, which is 3 to the 5th power, is not going to be involved. And so I take 99 divided by 81. I get 1 with a remainder of 18. When I try to have 18 divided by 27, obviously that's not going to work. I'm going to have 0 of that, and it's going to be the remainder of 18. I then divide by 3 squared, which is 9. And I end up with 2 with nothing that follows it. And so I have nothing to divide by 3, so it's 0, and the remainder is still 0. So the numbers are 1, 0, 2, 0, 0. And that's what the number is in base 3. 24, 27 in base 15. Here's my powers of 15. Obviously 15 to the 4th power is way too big. Actually 15 cubed is way too big. Neither one of those is going to be used. And so I'm going to start with 15 squared. So I'm going to divide this by 225. And I get a 10. Not to be alarmed, because remember 10, we do have digits we can use, which would just be the letters. So 10 with a remainder of 177. That 177 I'm now going to divide by 15, and I get an 11 and a remainder of 12. So I'm going to have a 10, 11, and 12. 10, 15 squares, 11 15s, and 12 singles. But again, these aren't digits in our base 10 system, but I represent them with letters of the alphabet for the base 15 system. So this is going to be A, this is going to be B, this is going to be C. So this is A, B, C in base 15. 1460 in the base 11 system. Here are my powers. Obviously 11 to the 4th power does not work for this. It's too big. So I'm going to start with 11 cubes. So I'm going to take 1460 divided by 11 cubed, or 1331. I get 1. Take the 129 divided by 121, the 11 squared, I get 1 with a remainder of 8. I take the 8, now divided by the 11, I get nothing. And then a remainder of 8, which I would divide by 1, which would give me just, 8. So what I have here is 1108, and that's what that number is going to be here. So it takes a good bit of division and some hand divisions needed, because you do need to know what the remainders are. There's ways of doing it on the calculator as well as for shortcuts go. But keep in mind that the divisions have to be carried through, and you have to be aware of remainders. So here we're asked to complete the following equation. So this is actually a little bit different, because you're asked to convert from one base to another, and it's not one of those aren't base 10. Like here I'm asked to convert from base 4 to base 16. Obviously, it'd be a lot more difficult to go right from base 4 to base 16 in direct route. So what I'm going to be doing is I'm going to first convert this to base 10, and then convert that base 10 number to base 16. And so to convert this to base 10, I have to realize these are all powers of 4. So it's, units, 4s, 4 squares, 4 cubes, 4 to the 4th, 4 to the 5th, 4 to the 6th, 4 to the 7th. And so I work that out. And I end up with 43,181 in base 10. And now I want to take this base 10 number, and I want to convert it to base 16. So now I have to be aware of my powers of 16. 16 to the 4th power is a bit too big, and so I start dividing by 16 cubed. So dividing this by 4096, I get 10 with the remainder of 3021. I take that and divide it by 256, I get 11 with the remainder of 205. I take 205 divided by 16. I get 12, the remainder of 13. And then this remainder would be then to be divided by 1, which would just give me 13 again. So, which means that it's basically equal to A, B, C, D in base 16. Here they have me do the exact same kind of conversion, except now I'm actually going from a higher to a lower one. So I'm still going to do it the same way. I'm going to convert the base 10 and then convert base 10 into base 7. So again, using these as my conventions here, I have basically, this is ones, 18s, 18 squares, 18 cubes, 18 to the fourth power. So I have 14 times 18 to the fourth power, plus 15 times 18 to the third power, plus 2 times 18 squared, plus 10 times 18, plus 11 times 18 to the 0, or just, 11. So that's what I have. I work that through, and I get this number here, 1,557,983 in base 10. Now I'm going to convert this to base 7. So now I have to be aware of my powers of 7. And I'm going to go to a quite high number of powers of 7, because 7 to the 7th power is 823,543, which is still smaller than this. I go to the next one, I'm too high. So I'm going to divide this by 7 to the 7th power first. And then take that remainder and divide it by 7 to the 6th power. And you can see how I'm working my way down through them. I'm not going to spend too much time going through the individual divisions. That's my 7 squared. I divide by 7. I get a 4 with the remainder of 0. So it's 161,46140. Now, when I have you do the additions, subtractions, multiplications, and divisions, they like to be able to carry them through without having to convert to base 10. Now, keep in mind, though, if you're stuck or you're unsure how to do the answers, you can resort to converting both numbers into base 10, carrying through the addition, and converting that back to whatever base you need to convert it to. So that is certainly an option. But we kind of talked about some shortcuts that I'm going to show momentarily here to try to do this without having to do that conversion to base 10 and then conversion back from base 10 again. And that's just being aware of what base we're in. We're adding two numbers that are base 6. And so, I have to remember that, once I get to, the digits in base 6 are 0, 1, 2, 3, 4, and 5. Let's put a bar here to kind of represent here, the space here. So, when I look at the first one, 4 base 6 plus 4 base 6, I kind of ignore the bases. I just say, okay, well, that's going to be 4 plus 4 is 8. Now, 8 does not exist in base 6. That would not be a digit. So this would be, the value of 8 would be a 2-digit number. So I'm going to have 1 6 and 2 1s. And so this represents a 12 in base 6. So this would give me a 2 down here and a 1 up here. Now I have 1 plus 2 plus 0, or just 1 plus 2 in base 6. And in base 6, 1 plus 2 is the same thing as it is in, base 10. It's 3. So I can just put the 3 down here. 3 plus 1 in base 6 is 4. And 1 plus 2 is 3. So the only time I have to really be concerned is when I start getting numbers that start going over 6 or more. That's when I have to go to the next level up. When I do a subtraction, of course, the main issue I'm going to have to deal with is borrowing. And so whenever I have to borrow, I have to be aware of what numbers are and what I'm actually bringing over. So for instance, I start with 8 minus 7, which is 1. That one's pretty easy. 8 minus 7 in base 13 is the same thing as it is in base 10, so nothing there. Now I have 1 minus A, which A represents 10. And I'm putting these other ones down here because we do have B and C later, so let's look for future reference. So here I'm trying to do 1 minus 10, which I'm not going to be able to do. And so what I need to do is essentially borrow 1 from B, which would make B is an 11, so that's going to make this a 10. And then I'm basically adding 13, because remember, I borrowed 13 from this. And so I'm going to have 13 to the third power plus 1 to the third, 13, that should be base 13. you know. Um, and then 13 plus 1 minus 10 is going to give me 4 base 13. And so, that's what goes here. Here I have 10 minus 4, which is 6. And then C, I have 12 and 3. Well, 12 minus 3 is 9. So 9641 base 13. For multiplication, it gets a little bit more complicated. Again, I mean, it's a base 14 here. So I do have to be aware of these numbers as well, which do cause its own complications. And for me to show some work down here, I'm going to like kind of carry it down here and eventually put the answer up here. So when I look at this, I have to do each multiplication separately and then kind of make sure I'm carrying things through. So 1 times C in base 14, 1 times anything is going to be itself. So nothing major happens here. So I'm going to have C, base 14. When I do 4 times C base 14, that's like 4 times 12, which is 48, which 48 is not a number in base 12. The 8th, of course, takes that completely out of there. So, or base 14, I should say. And so what I have to kind of do is say, okay, well, 48 is going to be 3 14s and 6 1s. And so, because 3 14s is 42, and so this is going to be 36 in base 14, which means I'm going to put a 6 down here and carry the 3. And so now I'm going to have B times C plus 3. So 3 base 14 plus B base 14 times C base 14, which is like basically like lowering the bases. 3 plus 11 times 12, which is 135, which again is not, it's a number in base 10. I got to put this back into base 14. And going through the same kind of process, of like dividing by powers of 14, is ends up being 99 base 14. So write the 9, carry the 9. And so now I'm going to have 9 plus 2 times C. And C is again 12. So I'm going to have 9 plus 2 times 12, which ends up being 33. And 33 base 10 is the same thing as 25 base 14. Now I'm not showing all the conversions that I did in previous problems because of space, but be sure you know how to get to these answers as we go through them. And so I'm going to write the 25 at this point here. Now I normally write a placeholder, so I'm going to put that 0 base 14 here. Now I'm going to do D times 1 to the 14th power, or 1 times D. And that's going to give me D to the 14th, so I just simply write a D down here. Now I'm going to do 4 to the 4 base 14th times D base 14th. And I'm just showing you all the work here that kind of goes through. I can show you, I can see like, I get 3A, 52, which is 3A base 14. Write the A, carry the 3. You can see all the work that gets done along with this. And then, of course, I have to carry through the addition, too. So I'm going to have, C plus 0, which is C. 6 plus D, there's all the work for that, carrying the 1. So I'm just going to like pause a moment so you can see all this work here. And you end up with the final answer, 2A, C6, 5C, base 14. Moving on to part D for the division problem. Now, most of the time you're not going to be given a 2-digit number to divide. You're just usually going to be given a single-digit number to divide because 2 digits are a little bit more difficult, and it's doing division with different bases. You have to kind of just keep things in the same base, because if you don't, then you get issues with remainders and stuff and how to convert those, and converting fractions and decimals in different bases is a whole other bag of worms. So basically, as you work this out, you have a base 6 number, so that means the only digits you can have are 1 or 0 through 5. So carrying out the multiplications that you would tend to see, you'd only be able to multiply. I mean, I'm not going to do 0 because that's still going to be 0, but multiplying by 1, 2, 3, 4, and 5 are the multiplications you would tend to see in using the long division of any kind of number. So these are the numbers that you would get if you carry through the multiplications. So with that in mind, carrying through long division as usual, The 5 is too small for 35, even base 10 or base 6. So 51. 51 is bigger, so we want to see how many times 35 base 6 can go into 51 base 6. And as you can see here, going in once would give you a 35. Twice would be 114. That's too big. So a 1's going to go up here. I'm going to subtract, and I would get 12. And just to confirm that, if you have 51 base 6 minus 35 base 6, you try to do 1 minus 5, you wouldn't be able to do it. So you'd have to borrow 1 from here, making that a 4. Now the thing is, when you carry this over, you're actually borrowing 6. So you would add 6 to this one. Now you could rewrite that in base 6 math. However, for base 10 purposes, it'd be the same thing as 7 minus 5, which would be 2. And that's in 2 in base 6. And then 4 minus 3 would be 1 base 6. And so this is 12 base 6, and hence that's where you get this here. Then you would bring down the 4, and you have 124. You can see that 35 could go into that twice, which would give you 114. 3 times would be 253. That's too big, so the next number is going to be 2. So 2 times 35 base 6 is going to give you a 114 base 6. Here we don't have to really do any major work done here because the subtractions are pretty straightforward. 4 minus 4 is still 0. 2 minus 1 is 1. 1 minus 1 is 0. So you didn't have to worry about borrowing anything, so that one works out pretty nicely. And then you would bring down the 2, making this a 102. Not quite big enough to be 114, so 35 will not go into this twice. It's only going to go into it once. So multiplying by that, and if you subtract, you would get 23 base 6, and just to kind of confirm where that came from, if you have 102 base 6 minus 35 base 6, again, you can't take 5 from 2, so I have to borrow 1. I actually borrowed 1 from the entire 10. Now 10 in base 6 is basically equivalent to 6, so if I borrow 1 from 10, I'm going to be left with 5. And I'm now going to add 6 to this, which is essentially 8. For our purposes of subtraction, I'm going to keep it in base 10. So 8 minus 5 is 3. And then 5 minus 3 is 2 in base 6. And so that's where the 23 base 6 is. And there's nothing else to divide. And so we would just say it's a remainder of 23 base 6. You could go on and do decimals if you want, but that gets a little bit more problematic along the way because you still have to kind of go through these numbers and see how well it fits and things like that. But that's how you would carry through the division for this. On to number 12. For number 12, they want you to use duplication and mediation. It's just a way of carrying through this multiplication. So basically the way it works is, again, you set this up with the left-hand number and the right-hand number. The left-hand number, you're going to be cutting in half each time. And the right-hand number, you're going to be doubling each time. And you keep doing that, and you ignore the remainder until you get down to 1 for this. So I'm going to have 121 and 142, cutting that in half. So that's actually 121.5, but I cut off to 0.5. This is 142 when I double it. So I ignore remainders. And I do the same thing all the way down until I get to 1. And now, I include this number up here. Now what I do is I look at anything that has evens. So 60 on the left-hand side. So the 60 and the 30 lines are going to go away. And so everything else has a left-hand column number of that's odd. And so I'm going to take those numbers that are left and add them all together. So 71 plus 142 plus 1136 plus 2272 plus 4544 plus 9088, and that comes up to 17,253. So obviously you could check this with a calculator along the way and just do 243 times 71 and you get the exact same answer. But you need to show the process, you need to show what you're eventually adding together. So make sure whenever you're asked to do this that you are showing sufficient work to show that you know how this system works if you're asked a question on it. Lattice multiplication, when you're multiplying numbers, again, you set up a lattice. So I'm going to have the 434 and the 29 down here. It's basically make these boxes, and I have these diagonal lines through them. And all I'm going to be doing for these boxes is like 4 times 2 is 8, so I'm going to put a 0, 8 here. 3 times 2 is 6, so 0 and 6 here. 0 and 8 here. 4 times 9 is 36, so a 3 here, a 6 here, so forth and so on. So when I carry those individual multiplications through, I have this. Now what I do is I start adding diagonally. So when I do this one here, that's my ones. So I'm going to have 6 ones. Here I'm going to have 7, 3, and 8. That's going to be 18 tens. I'm going to have 6, 2, and 6, which is going to be 14 100s. 3 and 8, which is 11 thousands. And I have no 10,000s, so I don't have to worry about putting anything out here. And so I carry these through. I have 6 plus 180 plus 1,400 plus 11,000, and that totals 12,586. Using Napier's rods, I mean, that's basically the same thing as lattice multiplication. So for me, in my respect to this, is if you're asked to do Napier's rods or lattice multiplication, it's the same thing. This Napier's rods is just a tool that actually had the lattices on them, and you can just match them up and accordingly, and then come up with the your diagonals that you can eventually just transfer over into a completed lattice, and then eventually add up your numbers together anyway. So I'm not going to really differentiate between the two because they're basically the same thing. So when I do 417 times 58, again, here's 4, 1, 7, the 5, and the 8. 4 times 5 is 20. 1 times 5 is 5, so 0, 5. 7 times 5 is 35. Same thing with the 4 times 8. 1 times 8, and 7 times 8 down here. And again, it's going to be the same thing. So ones, tens, hundreds, thousands, and 10,000s. And so just do some simplification. And then carry through the addition. I get 24,186, which if you carry that through, you'll on a calculator, you will see the exact same answer along with that. So modulo congruence. So here it's asking you to either give me a number that fits it or a number in the blank that makes this true. And some of them could have more than one answer. Some of them could have no answer, to tell you honestly. So 18 is congruent to what number modulo 4? Now in modulo 4, I mean, much like base 4 numbers, I only have 0, 1, 2, and 3 as my digits, as my numbers. So I want to see it has to be congruent to one of those 3, theoretically. And basically, all you're trying to, and all that number is basically the remainder you have when you carry through this number divided by your modulus number. So if I just do 18 divided by 4, I get 2 with a remainder of 2. This remainder is what goes in here. And any other number that would have a remainder of 2 when I carry through a division with 4 would be congruent to 18 as well. Same thing with 20 modulus 7. I'm going to take 20 divided by 7. I get 2 times 7, which is 14, remainder of 6. That 6 is what that number is there. Now for this subtraction problem, this multiplication problem, it's a little bit more complicated. I mean, theoretically, I still want to have a number that I put in there that is between, that's defined in the modulus system. So, like, for instance, modulus 6, I only have 0, 1, 2, 3, 4, and 5 as my digits. I want to hopefully find one of those that would work with this. And so, I want a number between 0 and 5 inclusive. So, I look at the number 5 and I want to say, okay, in modulus 6, what other numbers would be congruent to 5 in modulus 6? 11, 17, basically if I just go by 6 each time, 23 would be the next one, 29, and so forth. They would work. I can work my way backwards too. -1, -7, I should have other dots following this, but like for instance, a negative 13. Those would all be numbers that could also be considered to be the same thing. Can any of these be obtained by doing 4 minus some number that's in the modulus system? And the answer is, well, yes. I can get a -1 by putting a 5 in here. 4 minus 5 is -1. 4 minus 11 is -7. 11 I'm not going to have because of the fact that, it's bigger than 6. But 5 certainly does work. And so 4 minus 5 is congruent to 5 in the modulus 6 system. Seems kind of strange, you're saying like, well, 4 minus 5 is congruent to something with 5 in it. It's like the 4 is a 0. Well, not really. Um, just happens to be that, the difference of 4 minus 5, which is -1, would be congruent to 5 in a modulus 6 system. 8 times something equals 4 in the modulus 8 system. So I want to see, okay, well, I want some number between 0 and 7 inclusive. And so when I look at the multiples of 8, I have 8, 16, 24, 32, 40, 48, and 56. These are basically, taking the number 8 and multiplying it by each one of these digits here. When I look at numbers that are congruent to 4 in modulus 8, so it's going to be 4, 12, 20, 28, 36, 44, 52, and 60. Basically, I'm just going up by 8 each time with these. There's nowhere where I have the same number appearing in both of these lists. And that's what I'd be looking to do. I'm trying to find a number that would go in both of these lists because, these are obviously the multiples of 8. This is, times 0, times 1, times 2, times 3, times here. I mean, but none of these numbers, happen to be, multiples of 8, so there is no solution with this. And as a result, there wouldn't be anything I could put in there. Determine the measure of each angle of the regular polygon shown below. So here, you're using the formula that was mentioned in other things in the past. These are regular polygons, so we know that all the angles are the same measurement. This is a hexagon, so it has 6 sides, it has 6 angles. So I know that the sum of the angles is given to me by this formula, n minus 2 times 180 degrees. So for A, I'm going to have 6 minus 2 times 180 degrees, which becomes 720 degrees. And therefore, the measure of each angle will be 720 divided by 6, or 120. So each one of these angles I have up here is 120 degrees. When n is 8, for this octagon, I'm going to have 6 times 180, which is 1080 degrees, and divide that by 8, I get 135 degrees. So each one of these is 135 degrees. For this next problem, you're given an angle AAD and DAC are complementary angles. Angle BAC and angle EAC are supplementary angles. If the following are true, and you're given that the measure of angle EAD is 7x minus 4, the measure of angle BAC is 9x plus 18, what is the measurement of angle DAB? So there's a lot of things going on in this problem. Ultimately, I mean, you have the fact that, this angle here, EAD, and DAC, they're complementary, which means they should total 90 degrees. And we're going to get into like how that's going to help us in a moment. We're told that BAC, which is this angle right here, and EAC are supplementary angles, which means they should total 180. And we're given these measurements down here, which means that this is 9x plus 18. This is 7x minus 4. Ultimately, I want to figure out what the measurement of angle DAB is. So it's, this angle all the way through here. So there's a lot of intermediate steps here. So first off, I know the measure of angle EAD and DAC are complementary angles. So I know this is a right angle right here. Most importantly, that means that this is a right angle over here because they're supplementary to each other. This angle here, EAC and BAC, that was given right here. So this angle 9x plus 18 should be equal to 90 degrees, which means 9x should be 72, which means x should be 8 degrees. Which means that as a result of that, 7x minus 4, this measurement right here, should be 52 degrees. And if this is complementary with this angle right here, this angle up here should be 38 degrees. And since the measurement of angle DAB should equal the measurement of angle DAC plus the measurement of angle BAC, that's going to be 38 degrees plus 90 degrees, which should be 128 degrees. So that's what the measurement of angle DAB is. So a lot of things going on here, but if you're keeping things straight and using the right rules, not too much of a problem. For number 18, you're given that L is parallel to M, so these two lines here are parallel, and you're given that P is parallel to Q. So these two lines are parallel. So, these two lines are parallel. L and M are transversals of both of those. And same thing with L and M, with P and Q being transversals to those. You're given that this angle up here is 39 degrees. They want you to figure out what X is here. Now, again, there's different ways of doing this problem, and how I'm going to approach it is not necessarily the same way you would approach it, which is why it's important for, when you're asked to show your work, that you show the work, that you did to get this. So first I'm going to mark these as parallel lines, because I want to make sure I know that, that the rules I'm using are going to be applying to this, because if I have parallel lines cut by transversals, there are certain other things that I happen to know as well. For instance, this angle over here must also be 39 degrees. And the reason being is that that's a corresponding angle with, when I'm looking at lines L and M with P as the transversal, these are corresponding angles, and since these lines are parallel, they should be congruent to each other. So that's 39 degrees. Now when I look at angles, lines P and Q, this angle down here should be the same as this angle, because it's also a corresponding angle. Now with these two being the parallel lines and this being the transversal. And so I know that this angle is 39 degrees. These two angles are a linear pair and are supplementary to each other. Therefore, the measure of angle X plus the measurement of 39 degrees should total 180, which means that the measurement of angle X should be 141 degrees. So now there's different rules you could have used. You could have used other things along the way, but that's the way I approached it. There's different ways to get there, though. So for number 19, you're given that the measure of angle CBD is 72 degrees, so that's this angle CBD. BAE is 34 degrees, so that's this one right here. What would the measurement of angle BCD need to be in order for triangles ABE and DBC to be similar? So let's mark those two angles in there as we were told. Now, I know that this angle over here, being the vertical angle, also has to be 72 degrees. And I know that this angle up here has to be 74 degrees because the three angles inside triangle ABE needs to be totaling 180 degrees. Based on the way they're being named, angle A is supposed to correspond to angle D. Angle B is supposed to correspond to angle B, basically the middle, and angle E is supposed to correspond to angle C. So, so when you're asked, what does the measure of angle BCD need to be? BCD should be the same measurement as angle E, so this needs to be 74 degrees for them to have the same measurement, which means that the angle D should be the 34-degree angle in that smaller triangle. Now for part B, assuming that this is the case and that they are in fact similar, we want to be able to say, okay, well, what is the measurement of BC? Okay, so we have this triangle here, this bigger triangle, BAE, AEB, whichever way you want to call it. It has all three of its sides known. Triangle BCD does not have all three sides. It only has one side known. But I need to come up with a scale factor. If I come up with a scale factor, then I'll be able to figure out what BC is based off of what the corresponding side of this one's supposed to be. So when I look at this, this side here, CD, is opposite the 72-degree angle. That's going to correspond with AE on this one. Okay, so basically the scale factor, since they're similar, is that CD over EA should equal BC over BE. And I know the values of three of these. 8 over 24 should equal BC over 12. Now I could use cross multiplication, but I went with a simpler method here. I noticed that there's a division. It looks like a plus sign there, but that's actually dividing by 2. So if I divide by 2 in the denominator and I should divide by 2 on the numerator to keep the ratios the same, which means that BC should be 4 centimeters based off of the information that we have. Jim is standing outside on a sunny day. Jim is 5 feet 9 inches tall, and the shadow he casts on the ground is 23 feet long. At the exact same time of the day, an office building that stands 50 feet high will cast a shadow that is how long? So, first, let's deal with the issue that we have him having mixed units, and we like to keep all the units in the same respect. So I'm going to say that 5 feet 9 inches is basically the same thing as 5.75 feet, and I'm just going to leave it as that. And so what I have here is the sun. It's shining on Jim, and the shadow would be along here. I don't really express the shadow very much, but he's 5.75 feet. The shadow along here would be 23 feet long. We're assuming he's standing upright, and I have this angle being represented here just to kind of show that that angle is going to be the same for the building, because the sun is so far away that the sun, it should be striking the building and the person at basically the same angle. And that's what we're going to show here. It's at the same angle. This is theta. I don't have it marked on here yet. But, we know the building's 50 feet tall. We want to figure out what this shadow is down here. So, I don't know why I started over again. Putting them together, we know that they have this triangle here and this other triangle here, which are sharing this same angle here. And so what we basically have here is we have the 50-foot building. X represents this total distance here. And so, let me throw a pin in here. So X represents, okay, so I have a good color that you can actually see. Here we go. X represents this entire distance. Well, 23 represents just this distance right here. They are similar triangles that they have right angles. They share this angle, which means that this angle here and this angle here should be the same. They're similar. And so when I set up a ratio, I can say, well, this, X over 23 should equal 50 over 5.75, or another similar ratio to that. I have separated here, but 5.75 over 50 should equal 23 over X. I do some cross multiplication and get that 5.75x equals 1,150. And when I divide by 5.75, I get that x is 200. So the shadow should be 200 feet long. For 21 here, you're given this kind of odd-shaped figure. You're asked to find the area of this shaded region. You're asked to find the area of several shaded regions. For this one here, obviously the shape of its totality is nothing that I could possibly find on my own. But I do know that it's made up of, looks like, 2 right triangles and a rectangle. So when I see that rectangle up there, I do know that this side here is 8 yards. I don't know what the other side is yet, because I don't know. Let me get this pen off for a second. I don't know what this side is. I don't know what this side is. However, this being a right triangle, this being a hypotenuse, and this being the leg, I can figure out what the other side is. For the time being, I can call this x. And I know that x squared plus 7 squared should equal 25 squared. Working it all down using the Pythagorean theorem and some algebra, I do get that x is 24. So this is 24 yards down here, which makes this 24 yards. And so now I have everything I need to find the area of these 3 regions. Put some of these things back in. Don't know why I had to start over again. But, the rectangle is going to be 8 times 24. This triangle, since it is a right triangle, the legs are a base height pair, so 1/2 8 times 15. This is going to be 1/2 24 times 7. And as you can see here, I worked them all out. And when I add those together, I get 336 square yards. Now this one's kind of a little bit different because instead of adding things together, I'm going to be subtracting. I basically have the area of a trapezoid with the area of a circle being removed from it. So to start this off, let's kind of consider the trapezoid itself. I have a trapezoid. This looks like it's a right angle, and basically for these type of problems, if it looks like a right angle, you can assume it to be. That's usually not the best thing to do geometry-wise, but since this is not a dedicated geometry course, that's something that's not going to keep coming up. Basically, if it looks like it, it is. So this is going to be the height. These are the two bases. So when I find the area of this trapezoid, 1/2 the height times the sum of the bases, I get it's 126 square inches. I bring the circle in now. I'm going to subtract away this circle. Now, it being 4 inches here, not indicating a center or anything, this means that this is the diameter. So if the 4 inches is the diameter, it means that the radius is 2 inches. And the area of a circle is pi r squared, so it's going to be pi times 2 squared, which is 4 pi. And so for me to find the area in here, it's going to be 126 minus 4 pi, essentially. And that comes out to be 113.43 square inches approximately. For this one here, it looks like I have a right triangle and a semicircle. So I'm going to kind of draw a line there. One of the things I got to try to figure out is what is this length here, because that's going to give me the diameter of the circle. I also need to figure out possibly, I mean, I have enough to find the area of the triangle because I have the two legs. But I do need to figure out what this is so I can figure out what its radius is and then come up with the area of that circle. Or semicircle, I should say. So the triangle here, that's the base and the height. I have a semicircle here. But looking at this entire value here, x, this is the hypotenuse of this right triangle. And so if I figure out what x is in its totality, I should be able to figure out what this part here is, because this is 10 centimeters, this is 10 centimeters, whatever's left in here should be, add up to be the entire length that I'm marking as x right now. And right now, by the Pythagorean theorem, 18 squared plus 24 squared should equal x squared, which means that x squared is 900, x is 30. And so if x is 30, that means that this is 10, this is 10. When I get back to here, this part here should also be 10. So I know that the diameter of the semicircle is 10 centimeters, which means that I know its radius is 5 centimeters. And therefore, when I do the area of this shaded region, I'm going to have the area of the triangle plus the area of the semicircle. The area of the triangle is going to be 1/2 the base times the height, which is 216 square centimeters. The area of the semicircle is going to be 1/2 pi times the radius squared, because it's half of a circle, not a whole circle, which is about 12.5 pi square centimeters. So the area of the shaded region is going to be 216 plus 12.5 pi, which comes out to be about 225.27 square centimeters. Now for 21, all three parts, they give you a volume of shaded region to find the volume of. Be aware that surface area is also something you have to be aware of as well. I don't really think I have many problems with that. We'll see. I'm trying to remember. But we want to find the volumes of these shaded portions here. So this one here is pretty straightforward. It's just basically a cylinder with a cone on top of it. So the volume of this is going to be the volume of the cylinder plus the volume of the cone. The formulas for those are pi r squared h for the cylinder, 1/3 pi r squared h for the cone. Now the thing is, I have to be able to find the radius and the two heights. Now these heights, even though these are h's marked in the formulas, they may not be the same height, in this figure, because this is the height of the cylinder, this is the height of the cone. And when I look at these on the figure here, the radius, they share the same radius. I mean, they're on this. They have the same circular base, so they do have the same radius. That's fine. But the height of the cone and the height of the cylinder are two different things. So, and I got this 5 centimeters down here by knowing that this is the diameter and the radius should be half of that. So when I put in values for the h's, I have to make sure for the cylinder it's the 30 and for the cone it's the 15. So, make sure you're aware of what the symbols are in the formulas and make any accommodations you need to make sure you put the right numbers in at some point. So, um, so putting the right numbers in here based off of what we found out in this figure, I end up with 750 pi plus 125 pi, which is 875 pi cubic meters, and that's approximately 2,748.9 cubic meters. For B, I have which basically here is a trapezoid-based prism. Knowing it's a prism, I'm going to find the volume by pretty much the same way I would any other prism. The other thing that's going to be different is, finding the area of the base is what gets to be complicated because the base is, whatever the shape of the base is going to determine what formula I use to find that area. And so when I look at this, I have the base, this is trapezoid. This one down here would be the height of the prism. So right now the volume would be the area of the trapezoid times 41 centimeters for the height of the prism. Now let's focus on that base, that trapezoid, which the formula for the area is 1/2 the height times the sum of the bases. Now, this height is not the same thing as this height. This height means the height of the trapezoid, so the trapezoidal base. So I have to be aware of that. So when I look at the trapezoid itself, I know that this side here is 30 centimeters because it should be the same measurement as this. This is 20 centimeters, and this is the height of that trapezoid. Okay, so there's two different heights in this again. I have to make sure I know which one's which and where they need to go. And so this is 26, that's the height, 20 and 30. So 1/2 26 times 20 plus 30. I end up with this, which is 26,650 cubic centimeters. And for the last part of this, you're given this, the shaded region actually is now, in this case, a pyramid with a sphere inside of it. And so basically the sphere is taking up space. The shaded region is basically everything inside the pyramid except that sphere. And so what you have a square-based pyramid, which will always kind of look like it's a parallelogram down here, but it's a square-based pyramid. We usually don't do many sophisticated shapes for the pyramid because they cause some crazy things with the faces of the pyramid. The height of the pyramid is 30 feet. The diameter of the sphere is 40 feet. So basically to find the volume of the shaded region, the shaded portion, I'm going to do the volume of the pyramid minus the volume of the sphere. The volume of the pyramid is calculated by doing 1/3 the area of the base times the height. And so the height of the pyramid is 30. The area of the base, since it's a square base, is 60 by 60, which is 3,600 square feet. So I have 1/3 times 3,600 times 30 minus the volume of the sphere, which is 36,000 times minus the volume of the sphere. Now the sphere, its formula is gotten by doing 4/3 pi r cubed. I know the diameter of the sphere is 20, which means that the radius is 10. So substituting that into for r, I end up with 36,000 minus 4,000 pi over 3, which is approximately 31,811.21 cubic feet. And that is the end of this video. If you have any further questions, please make sure to reach out and ask me about it. Until next time, have a good day.